Hi everyone, it's Radha. I'm the LC leader for Dr. Clemens' class this semester for Orga 1, and I just wanted to make a little video on ranking acidities, that like rank in order of increasing, decreasing Ka, pKa, that sort of question, and just talk about the whole concept of ARIO in general, because I noticed there was a lot of contention about this topic in LC, and so I thought it would be helpful to just make a video and share it with you guys. Please let me know if this doesn't make sense to you. I can try and find another way to explain to you. But I really hope it does because this is, I've given this like spiel many times. So yeah, let's get into it. Please do reach out to me if you have any questions or anything. Okay, let's talk about acids. So in Gen Chem, we learned about Bronsted-Lowry acids, right? Which is where, like in this example right here, our base gains a proton from the acid. So we talk about it like the acid is the one that wants to give away its proton and the base is the one that wants to get the proton. That's Bronsted-Lowry. In Orgo, we talk about Lewis acids, and that has to do with electrons. That's really the foundation of Orgo. All of Orgo is about electrons. So once you can internalize that, it starts to make a lot more sense. Okay, so if we were to look at this from a Lewis acid perspective, we would look at our A, by the way, just stands for like any arbitrary group that is an acid and then becomes a conjugate base. That's just what A, it's just anything. Okay, so let's draw some arrows for this one right here. Let's use pink. Okay, so if we were to look at this from a Lewis acid perspective, the lone pairs on this oxygen would be going over. Oh, that's an ugly arrow. They would be going over, grabbing the hydrogen, and these electrons that make up the bond between the hydrogen and whatever carbon it is that it's connected to, they're going to break off and sit on the other part, the A, right? They're gonna break off and they're gonna sit on the A as a lone pair. So that's what our conjugate base has. Remember, the acid has a conjugate base. Acid, conjugate, base. You can also remember that strong acids have weak conjugate bases. Remember, strong acids, the 7 ones that you learned in Gen Chem. Now our definitions of strong acids are a little bit different, but that concept doesn't change. The fact that strong acids have weak conjugate bases and weak acids have strong conjugate bases. What does this mean? Well, strong acids are strong because they're reactive. That's what strong means. So they're reactive. They want to get rid of that hydrogen and they want to become a stabler conjugate base. So a strong acid has a stabler conjugate base. It has a weaker conjugate base. Stable correlates with weak, okay? Weak meaning not reactive, right? So strong acids are reactive. They want to give away their hydrogen. That's what we learned. So strong acids, when they have weak conjugate bases, they have weak conjugate bases that have negative charges. So what we mean when we say we have a weak, stable conjugate base is that we have a conjugate base that's well able to stabilize that negative charge. That's what we mean when we say we want to find the stablest conjugate base. So I'm going to write this down big because it is very important. Strong acids have conjugate bases that are stable with a negative charge on them, okay? That is the bottom line of this whole ARIO situation. Speaking of that, let's talk about them more specifically. So what we want to do is find factors that make this conjugate base stable with a negative charge. That's what ARIO is. There are 4 factors that can stabilize a negative charge. And if we can find the stablest one, we will know which one came from the strongest acid. Let's dive into it. So A stands for atom, R stands for resonance, I stands for inductive effect, and O stands for okay. Those of you who come to my LC, you know that my computer is always glitching. Orbital or hybridization. Okay, so that's what the orbital stands for. It's more about hybridization. Okay. So atom, what does that mean? there's two things that correlate that come inside the umbrella of atom, and that is size and electronegativity. So I am going to give 3 arbitrary examples of potential acids, and we're going to rank them. Let's say you have SH2, OH2, and NH2. Okay, so the first thing we do when we want to rank acids from, strongest to weakest is deprotonate them. That's what we learned with the Bronsted-Lowry bases, right? We want to deprotonate them, or we want to take away the hydrogen. When we talk about Lewis bases, we're talking about the electrons coming back down onto the hetero atom. So what I mean by that is once this H is taken away, right? These electrons need somewhere to go, so they're going to settle on the hetero atom that they're connected to. So you're going to have your lone pair on this sulfur, and your sulfur is going to have a negative charge. So same thing happens when we deprotonate the other ones. Okay, now we have all of our conjugate bases that came from our 3 acids. So let's look at the differences between all of these conjugate bases. If we go to the periodic table, we can see that sulfur is right below oxygen, and oxygen and nitrogen are right next to each other. Let's think back to Gen Chem 1 to our periodic trends. Remember that electronegativity increases this way, and atomic radius increases in the opposite direction, right? Atomic radius, or size, increases in the opposite direction. So let's think about what these two terms mean. Atomic radius is the size, right? It has more space for, let's say it has more space for the electrons to sit, right? So that's what atomic radius means. And electronegativity means that the atom is more comfortable holding a negative charge. So it wants to hold the negative charge. That's what electronegativity means. So if we look at between sulfur and oxygen, right? Sulfur is it's bigger than oxygen, but it's less electronegative than oxygen. And nitrogen is bigger than oxygen, but it's less electronegative than oxygen. So how are we supposed to rank these, right? So let's look at it more closely. The size difference between oxygen and sulfur, because they're in completely different rows, is going to be much greater than the size difference between oxygen and nitrogen. So when we're looking between oxygen and sulfur, size matters more. So when you look at things between rows, size matters more, and sulfur is going to be more comfortable with a negative charge than oxygen is. But when we look between oxygen and nitrogen, because they're in the same row, the size difference is not that big, so electronegativity is actually going to matter more. So oxygen is stabler with a negative charge than nitrogen is. So if we go back to our 3 conjugate bases here, sulfur is bigger than oxygen, so it's the acid that it came from is going to be stronger than the acid that this one came from, right? And that's going to be stronger than the acid that this one came from. So there we go. We have them ranked based on size and electronegativity. Remember, if they're in 2 different rows, size matters more, and if they're in the same row, electronegativity matters more. That's just a good rule of thumb. It's never failed me. Rank these two. We want to see which of these 2 acids is more acidic than the other, right? Okay, so the first thing we're going to do, just like we did last time, is we're going to deprotonate both of these. Sorry, I should have drawn this in green. We're going to deprotonate both of these, give them a negative charge. Now, what can happen with the one here on the left is this negative charge it's lone pairs, right? It has the capability to move here, break this pi bond, and push those electrons up there. So what you get is a resonance structure that looks like this. And now we have the negative charge, or our lone pairs up here. You will be asked to do this sort of arrow pushing and draw resonance structures on your quiz. So there are more complicated examples in like your practice problems. So make sure you do those too. Okay, now let's look at this one. The lone pairs on this oxygen, they don't really have anywhere to go, right? They're stuck where they are. They're not delocalized. Whereas this one, when you actually combine these 2 resonance structures, you get something like this, where, you get something like this, where that negative charge is actually shared between the two oxygens, which helps stabilize it. So something with electrons resonating is going to be stabler, like a conjugate base with electrons resonating is going to be stabler than a conjugate base. Oh, what just happened? On me, but basically I was saying that something with resonating electrons, like this structure right here, is going to be more stable with a negative charge than something without resonating electrons because it's sharing that negative charge. So that means that the acid that this conjugate base came from is stronger than the acid that this conjugate base came from. So that's resonance. Now let's do inductive effect. I strongly urge you, if it hasn't been making sense, go back and rewatch the video a couple times, and I think the more you listen to it, the better, the more it will make sense. Okay, let's look at two structures. I'm going to put them in green, actually. Let's look at two structures. Let's look at this and this. Okay, so immediately you can kind of infer what this is going to be because you see that this guy has a fluorine and the other one doesn't. But let's go about the method of deprotonating everything first. So when we add that negative charge there, we recognize there are lone pairs here that are creating that negative charge, right? Which one do you think is going to be stabler? If we go back to the periodic table, what is fluorine? Fluorine is the most electronegative atom on the periodic table. That's what fluorine is. So fluorine, chlorine, even bromine, they can all kind of contribute to this. It's called the inductive effect. What happens is these electrons, they exist in their clouds, right? What fluorine can do, because it's electronegative, is kind of pull on that electron density and stabilize the negative charge that the lone pairs create. So something with an electronegative atom nearby to the negative charge, it does something called the inductive effect, and that stabilizes the negative charge. So something with induction is going to be stabler than something without induction. So the conjugate, so this conjugate base is going to be stabler than this one. So the acid that this one came from is stronger than the acid that one came from. Okay, now let's do orbital. So orbital means hybridization, which if you don't remember at all, I would highly, highly, highly recommend going back and learning about it more. But let's look at these hydrogens here. Which one is going to be more acidic? It all depends on something called S character. S character, do you guys remember all of those orbitals? Like this is S, this is P, there's also D, F, right? Those are all different orbital shapes. And if you remember those molecular orbital diagrams, the S orbital is stabler than the P orbital. So this circular S orbital is stabler than the P orbital, which is intuitive, right? The shape, by just the shape. So something with more S character is going to be stabler than something with more P character. What does that even mean? Okay, so at this carbon, right, the hybridization is sp3 because it's attached to 4 different groups. So the hybridization there is sp3. Whereas at this carbon, the hybridization is sp2 because it's attached to 2 different groups. So S character means here you have 1/4 S and 3/4 P, right? Whereas here you have 1/3 S and 2/3 P. Which one is there more S character in? There's more S character in the sp2 orbital. There's a greater proportion of it because 1/3 is bigger than 1/4, right? So where you have more S character, you will have a stabler situation there. And so this is the stronger acid than this. I hope that makes sense. Okay, let's go and do a practice problem, so this is all of ARIO. Those are the 4 factors that come into play in ARIO. A lot of people say ARIO is the order, but that's not true, and I'll show you why in the practice problem that we go through. Okay, the way that I go through these is by first looking at what each hydrogen is attached to and then ranking them based on that. So this question is saying rank hydrogens A, B, C, D, and E in order of increasing pKa. Okay, let's actually talk about that first. Increasing pKa. A lot of people get tripped up when they see the P in front of something. P is nothing but a function. So the P of x is the negative log of x. That's why pH is the negative log. pH is a negative log of your hydrogen concentration, right? So pKa is the negative log of your Ka. That's all. That's all that P even means. So Ka, we know that as Ka increases, the strength of your acid increases. And that's because of equilibrium, products over reactants. If you don't remember that, please just reach out to me and I can explain it. But yeah, the higher the Ka, the stronger the acid. So because the P function includes a negative sign, it's opposite for P of something. That's why the lower your hydrogen concentration is, the higher your pH is, right? It's inverse. So in this case, increasing pKa means we're going from low pKa to high pKa, right? So that means low pKa is a stronger acid, high pKa is a weaker acid. So we're going from strong to weak acid here. Strong acid. Oh, wow, that's a huge marker. Strong acid to weak acid, okay? That's what we're looking for in our ranking. Don't miss points on those. It's very easy to miss points on that label of increasing, decreasing, pKa, Ka. So be very careful and vigilant about that. Okay, what I meant earlier is that I like to look at things that are connected to each hydrogen. So for example, I'm going to compare A and B because they're both connected to carbons, and I'm going to compare C, D, and E because they're both connected. All three of them are connected to oxygen. So first, when we compare A and B are different because here there is a pi bond and here there is a sigma bond. So what's going to happen is the hybridizations are going to be different, and this relates to the whole orbital concept, right? So here our hybridization is sp2, and here it's sp3. And we said that the more S characters something has, the more acidic it is. So the A is going to be more acidic than B. So we can say A is more acidic than B, right? Okay. So then let's look at C, D, and E. Let's deprotonate all of these. Let's use a different color. Let's deprotonate all of these. Deprotonate, deprotonate, deprotonate. Now we have negative charges sitting on all of them. So we want to try and see which one is the stablest. So we can see that between these two, the difference is the other thing connected to the carbon. So here we have a hydrogen, here we have a fluorine. That ties back to inductive effect, right? If we have something electronegative near the negative charge, it's going to help with that electron density. So that makes this stabler than this, which means when we reprotonate it, C is going to be stronger than D. So we can say C is stronger than D. Okay, now let's look at C and E. I don't know why I removed that. Okay, E, what's going on at E? The beautiful thing that we know as resonance, right? So we have resonance at E. These lone pairs, they can come and connect here, break this pi bond, and push those electrons up onto the oxygen. So here we have the negative charge being shared between, sorry that my computer is glitching so much. We have the negative charge being shared between these two oxygens, right? My computer is giving out on me. Okay, so because we have resonance here, we can say that this was a stabler conjugate base than C, And this is going to be the stronger acid than C. So we can say that E is stronger than C is stronger than D. Okay, now let's look between this set and this set. We know that, remember the whole concept of atom, that the negative charges on oxygen are already going to be stabler than negative charges on carbon because oxygen is a more electronegative element and they're in the same row, right? So we already know that anything connected to an oxygen is going to be more acidic than anything connected to a carbon. So we can just put this whole group in front of this group. So we get our final ranking as E, C, D, A, B. And that should be the correct final answer. So yeah, that is ARIO. There are more examples. There's tons of examples in your practice problems. Please do them. It's a very important concept to just understand, OChem in general. And it's definitely going to show up on quizzes or tests. But yeah, I hope that was helpful. Sorry, my computer was so glitchy and I had to cut it in the middle. But yeah, please let me know if you have any other questions or need anything from me. You can just email or text me or come talk to me in LC or class. But yeah, good luck studying, and yeah, bye-bye.